Welcome back to KSET previous year question and solution classes. Today in this class I am going to discuss condensed matter physics or solid state physics or material science part. So this is 2015 paper. So the question is like this: when a molten zinc is cooled to a solid state, it crystallizes in HCP. It crystallizes in HCP, hexagonal closely packing structure. The number of nearest neighbor of zinc atom will be. Number of nearest means, if in the structure, for example, let us take a simple cubic. If suppose this is our a reference lattice point, for this reference lattice point, how many number of nearest lattice points will be there? Nearest means a very nearer to this lattice point. And for simple cubic, see, for simple cubic the number of nearest atoms or lattice points is 6, for BCC it is 8, and for FCC it is 12. 12 nearest lattice points will be there, and for HCP it is also 12. For FCC and HCP both are same, and this is nearest neighbor distance for simple cubic and BCC, body center cubic lattice, and face center cubic lattice, and for HCP. Okay. So, but there is no options related. Okay, this is 12. The D option is 12. Okay. So, answer is D. D is the correct option. So, this is question number 56. A substance AXBY crystallizes in FCC lattice form in which A atoms occupy each corner of the cube and B atoms occupy the center of each face of the cube. Identify the correct option of the substance AXBY. See, for example, this is our cube. In the cube, see, these are our corner atoms. These corner atoms occupies A type of lattice, and so these are our face. So the face of the cube occupies B type of an lattice. So now what is the composition? It is a very easy question and a very logical question. See, we know that identify the correct options of the substance AXBY. Here AXBY, we have to calculate number of lattices in a unit cell, in a cubic of BCC unit cell. We know that in a BCC unit cell, number of lattice is 1 by 8 into 8 plus 1 by 3, 6. Okay. So, yes. So, 1, 2, 3, 4, 5, 6, 6 by 3. So, each corner atoms, so each face atoms occupies 2 other. So, 6 by 2, sorry. So, this is 6 by 2 because each face occupies each share another FCC structure, right. So, this surface share with another FCC structure, this surface share with another FCC, and this surface share with another FCC, and this surface face another FCC. So, therefore, 6 by 2. So, which is equal to this is for corner and this is for face center. So, for corner atoms 1 by 8, 8 is 1, and for face atoms 2 3s are 6. So, plus 3 is equal to 4. So, which is A1 and B3. So, total 4. So, this is the composition. Number of lattice in a unit cell is 1 for A. A atoms occupies corners, and number of lattice points for B is 3 because B as share with 6 another faces. So, A, B, 3, option number C. So, option number C is correct. Okay. So, this is the question number 57. The structure factor of a single cell of identical atoms of form factor is given by SHKL. So, F into summation j e power minus 2 pi I and H xj plus k yj plus L zj. So, where x j comma yj zj are the coordinates of an atom and h comma k comma L are the Miller indices. Which of the following statement is correct for diffraction peaks of BCC and FCC lattice? So, the question is so big and options is also so big, but solutions is very easy and very logical. So, let us see how we can guess the given in the answer for the given option. Okay? See. So, this is the explanation for these options. See, for a simple cubic cell, all values of h comma k comma L are allowed. That means, see the next explanation, h comma k comma L are all odd or all even, and h plus k plus L should be divisible by 4. So, this is the condition for DCC, diamond cubic structure, and for BCC, body centered cubic structure, h plus k plus L should be even. It should be even for BCC, and FCC, h comma k comma L should be unmixed. All or suppose all are odd or all are even. See, for example, in BCC, if we add 2 plus 1 plus 0, 2 plus 3 is 3. So, that means, but our condition is for BCC, if we add h plus k plus L, it should be even. It may be 2 or 4 or 6 or 8, something like that. But here we get 3. So, this is not a correct option. Here we will get 2, here we will get 6, but in the first BCC group, in the first Miller indices group, we will get 3. So, this option is not correct. And FCC 1 1 1, okay, all the 3 are either odd or either even. Here also all the 3 Miller groups are odd. So, okay, all the 3 groups are even, okay, but BCC is not satisfied. So, this option is not correct. Okay. Next, for BCC, option number B, 2 plus 0 plus 2, 2, 1 plus 1, 0, 2, and 2 plus 2 plus 2, 6. See, if we add h, k, L, we will get 2, 2, 2, 2, 2, 6. So, all the terms are even, so it is satisfied. Next, here for FCC, 1 plus 1 plus 1, 3, and all the 3 Miller indices h, k, L are odd. It should be either odd, it should be either even, but not mix. Here, odd, 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 okay, even, 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 okay. So, no problem. So, B is correct answer. So, coming to the C, 2 even, 1 plus 1 2 even, 2 plus 2 plus 2 even. So, this is correct, but in FCC structure 1 1 1, okay, but here one is even term, another one is another 2 is odd term. So, here there is a mixture of even and odd terms in this FCC group. So, this is not a correct option and this is okay. Here 2 plus 1 3. So, if we add h plus k plus L, it should be a even number. So, this is not correct option. And FCC, It is also mixture of even and odd. So, this is also not satisfied. So, option B is correct. So, this is the question 58 question number. The total specific heat of a metal at temperature is plotted as a function of temperature, which is shown in the figure below at low temperature. See, so this concept comes under heat capacity of a metal. Okay. So, the actual graph for this heat capacity of a metal is like this. See. So, this is the actual structure of the graph. This is an example for a potassium I am taking. Actually, the specific heat, the electronic specific heat is obtained by sum of electronic and phonon, sum of electronic and phonon contribution. So, C is equal to gamma T plus A T square, or C by T is equal to gamma plus A T square. C by T is linear to T square, where gamma is intercept. So, like that, in the given option, the slope of the graph, so that means this indicates the slope of the graph or the y-intercept or CV by T at theta T is equal to theta D, where D is the D by angle and the x-intercept, and this is y-intercept. Okay. Option number B is correct. Okay. So, this is the question number 59. The electrical resistivity of a metal at 300 Kelvin is 4.9 into 10 to the power of minus 8 if the Lorentz number is 2.45 into 10 to the power of minus 8. The thermal conductivity of the metal will be, these are the given options. Okay. See, according to Wiedemann Franz law, and this concept is very important for K-set. See, for K-set, from the chapter free electron theory of model, at least 2 to 3 questions will be there for every year. Okay. Hall effect, Wiedemann Franz law, and that previous one we solved, right, the specific heat of a metal. So, that question is also from the free electron theory of metal. Okay. So, this chapter is very important. This concept is also comes under that free electron theory of metal. So, Wiedemann Franz law states that for metals at not too low temperature, that means at not a very too low temperature, the ratio of thermal conductivity to electrical conductivity, this is very important. The ratio of thermal conductivity to electrical conductivity is directly proportional to the temperature, with the value of the constant of proportionality is independent of the parameters of the metal. And the equation, the mathematical expression is K by sigma is equal to LT. So, let us substitute the constant values here and let us see what will be the answer. Okay. So, the electrical resistivity is given. This is electrical resistivity. Rho is equal to 4.9 into 10 to the power of minus 8. The temperature is given, T is equal to 300 Kelvin. Okay. And the Lorentz number is given, that is L is equal to 2.45 into 10 to the power of minus 8, and the thermal conductivity we have to calculate. So, what is thermal conductivity? K. K we have to calculate. So, therefore, K is equal to, from the expression, LT sigma, since sigma is equal to 1 by rho. So, K is equal to LT by rho. So, therefore, what is L? 2.45 into 10 to the power of minus 8 into what is T? 300, and what is rho? 4.9 into 10 to the power of minus 8. Minus 8 cancel, and this 2.45 is approximately equal to 2.5, and this 4.9 is approximately equal to 5, and this is 3 into 10 to the power of 2. So let's see, if you multiply with 3 with this 2.5, it will becomes 5 3s are 15, 5 1 carry, and 3 2s are 6 plus 1 7.5 divided by 5. So if you solve this, 5, let us take 75 by 5 into 10 to the power of 1. So here 10 to the power of 2. So 5 15s are 15 5s are 75, right? So 15 into 10 150. So 150 is the answer. So is there any 150? Yes. So 150 is the correct answer. Next, question number 60. It is difficult to determine the Hall coefficient for a metal as compared to a semiconductor because the Hall coefficient will be small, Hall voltage will be very high, and Hall effect will not be exhibit in metal, and Lorentz force will not act on a free electrons. So it is very difficult to determine Hall coefficient because for a metal compared to semiconductor, Hall coefficient will be small, too small. In the earlier class we discussed already, Hall coefficient means, so Hall effect means, so an electric field is developed in a particular specimen when it is placed in an electric field and magnetic field. When you apply an electric field between the two surfaces of a metal and there is a magnetic field, so in that an electric field is developed, that is called Hall effect, and that is very small for a metal compared to semiconductor. So option number A is correct. Question number 62. Due to breaking of periodicity at the surface of a semiconductor, okay, so options: impurity states are created in the band gap, or doping of the semiconductor takes place, or surface states are created in the band gap, or extended states are created in the band gap. So answer is C, surface states are created in the band gap. Okay. Next, so question number 63. In an indirect band gap semiconductor, for an electron to get excited to a conduction band, only when a photon of energy is higher than the band gap energy is required, or a phonon is required, or a photon of energy higher than the band gap and a phonon are required, a phonon unrequired. Sorry, this is not an option. So answer is C, a photon of energy higher than the band gap and a phonon are required. So option C is correct.